Assalamualaikum and good day everybody. So today I'm going to continue with the vibration topic, and now we enter a new subtopic which is damp vibration. So we have learned about free vibration and forced vibration. So now we want to add damper to both free and forced vibration. So what will happen in the equation, we will see that in this lecture, right? So every mechanical system possess some inherent degree of friction. So it is impossible to have friction-free system. So if any motion included in the mechanism, of course there will be friction in real life, but if we do in calculation, yes, of course we can ignore the friction, but in real life friction always occur, friction always exists. So friction will dissipate the mechanical energy, and it act like a damper. So this is the one type of damper which is unintentional. So sometimes we don't want this kind of damper, or we want to minimize it. So there is another type of damper which is intentionally. So we add dashpot. Dashpot is is a good damper, or viscous damper. It is intentionally added to a system to limit or retard vibration. So sometimes, for example, we can see in car suspension, where we have a spring and we have dashpot as well, because we don't want our car to vibrate, have a high vibration, and it will cause uncomfortable feeling. So that's why we have dashpot to damp the vibration. Alright. So simple dashpot range as shown as a force where the magnitude is proportional to the velocity. So we have learned about this, where dashpot or damper, its magnitude force is proportional to the velocity of the mass. So we have a system right here where we have spring and dashpot and a mass. So C is the viscous damping coefficient, or damping coefficient for short, and its unit is Ns over M. So what is Ns? S over M is actually is Newton per velocity. Newton per velocity. Alright. The direction of the damping force of the mass is negative Cx dot. So the direction of the damping force always against the motion. So right here, this is the motion of the mass. So the force from the dashpot is this way, and same goes to the force from the spring. Okay. So this is the free body diagram. The red color is the free body diagram. The red arrows. So we have force, reaction force, weight. We have force from the spring and from the dashpot. And the blue colored arrow is the kinetic diagram. Kinetic diagram. So that is the direction of the acceleration, where the direction of the acceleration always similar or positive with the direction of displacement, right? Okay. So from this diagram, we can compare the free body diagram with the kinetic diagram. So again, this is the free body diagram equation. We consider the horizontal direction only, and this is the kinetic from the kinetic diagram. So notice the negative sign. Negative is because it is in direction against the displacement. So when we rearrange it, we can get this kind of equation: mx double dot plus kx plus c x dot. So this is the new term that we learned today. Alright, the equation can also be written as in terms of the natural frequency right here. So, but since this is the new component that we learn, okay, we have a little different. Okay, so what is the how to get this component? This one. And we have new parameter, which is zeta. So zeta is an important parameter in this case. It's called viscous damping factor or damping ratio, and it measures the severity of the damping. Okay, so what is zeta? Zeta, this is the formula of zeta. Actually, you can get zeta from this equation. So actually, you divide everything with m. Alright. So when you divide everything with m, you will get to 0. So you know that k over m is equal to omega n square, and alright. So and right here, okay, we can replace it with c n square over k x dot. So from this component we can get this one. Alright, so remember cwn square over k. So c w omega n square over k wait, so that is for this component. Alright, so we replace with zeta. So since we know zeta, wait